In this video, we will discuss importance of Dirichlet's conditions in the expansion of Fourier series. Not all functions fx can be expanded as Fourier series, but only those functions which follow a set of conditions known as Dirichlet's conditions can only be expanded as Fourier series. Let us study about this in detail. Hello friends, welcome to channel Number Collage. This channel is dedicated to videos on a wide range of mathematical concepts and problems related to them, ranging from high school math to engineering math. Effort has been made to explain the concepts through basic mathematical ideas in a simple English. Hope you will like my effort. Thank you. It should be kept in mind, Fourier expansion of fx in each case shall not be valid, given the fact that expressing any function fx as a Fourier series depends upon evaluation of the integrals 1 upon pi integral f of x cos nx dx and 1 upon pi integral f of x sin nx dx within the limits 0 to 2 pi minus pi to pi or alpha to alpha plus 2 pi. Accordingly, fx should be defined for every value of x in the same interval, that is, in the intervals 0 to 2 pi, minus pi to pi or alpha to alpha plus 2 pi. Therefore, any function fx can be developed as a Fourier series f of x equals a0 upon 2 plus summation an cos nx n from 1 to infinity plus summation bn sin nx n from 1 to infinity, where a0, an and bn are constants, provided a f of x is periodic, single valued and finite, b fx has finite number of discontinuities in any one period, and c fx has at the most a finite number of maxima and minima. According to first condition, sin inverse x cannot be expressed as a Fourier series. This is because it is not a single valued function. As we know, sin inverse half is pi by 6 and also sin inverse half is 5 pi by 6 in the period 0 to pi. Because it is not a single valued function, in terms of curve of a function, if a function has a rectangular shape curve like this, here integral fx from 0 to pi is this area a and this width is pi. So this area will be a into pi, which is less than infinity or finite. Here, since fx obeys first Dirichlet's condition, it is absolutely integrable and its Fourier series can be written. Now consider function fx equals tan x, whose graph would look like this. In this case, integral f of x dx from 0 to pi by 2 will be integral tan x dx from 0 to pi by 2 will be infinite, because as x approaches pi by 2, area will be infinite, and since tan x is not absolutely integrable between its domain 0 to pi by 2, tan x cannot be expanded as a Fourier series between 0 to pi by 2. Same is the case with domain from minus pi by 2 to 0. In short, tan x cannot be expanded as Fourier series in the domain minus pi by 2 to pi by 2, because these integrals are not finite. According to the second condition, f of x has discontinuities finite in number in the given range of domain. In the first graph drawn here, there are two discontinuities. The first is here, because at x equals a, there are two values of fx. First is f1 of a and second f2 of a. Same is true for The second discontinuity at x equals b, because the value of fx breaks at x equals b from f of b here to say f1b to f2b here. So since there are finite number of discontinuities of this function, its expansion can be expressed as a Fourier series. In case of second graph of function fx, x equals c is a point of finite discontinuity because the graph breaks at f1c here and f2c here. Therefore, in this case, expansion of fx as a Fourier series is possible. When we say that x equals c is a point of finite discontinuity, both the limits of fx, limit fx as x tends to minus c, that is the left hand limit, and limit fx as x tends to c positive, that is the right hand limit, both exist at such a point. Fourier series gives the value of f of x at x equals c, that is f of c equals the arithmetic mean of these two limits, that is half times limit fx as x tends to c minus plus limit fx as x tends to c plus. According to third condition, fx has finite number of maxima and minima in the range of given domain. To understand this, let us consider graph of function fx, which is in the form of sawtooth shape. In the domain of minus pi to pi, it has one minima, and in the domain of 0 to 2 pi, it has one maxima here. Since fx has finite number of maxima and minima, function fx can be expressed as a Fourier series. So the third Dirichlet's condition is also satisfied here. It should be noted that not all the functions fx can be expanded in the form of Fourier series, but only those functions that follow a set of conditions known as Dirichlet's conditions. What are those conditions? Number 1, fx has finite number of maxima and minima over the range of time period. Second, fx has finite number of discontinuities over the range of time period. And thirdly, fx should be absolutely integrable over the range of time period. Viewers, if you like this video, please click the like button. Share this video with your friends and classmates. Subscribe to this channel. Post your constructive comments to make the videos better. You can even check playlist of this channel. Perhaps you might find videos that you are looking for. See you in the next video. Until then, keep watching Number Collage. Thank you.